So the work I'm going to present is from an article that we put out on the archive late last year. Now it's in the process of being published with two of my collaborators, so Christian Agendorf in Louvain-la-Neuve and Luigi Cantini in Cergy-Pontoise. And I'm going to tell you about specific computation of a correlation function, the boundary emptiness formation of probability. And it's going to be in actually two models, the six-vertex model at a very special point, the combinatorial point, and also the XXZ spin chain. So there you go. All right, so the outline of my talk will be as follows. It's going to be in 5 parts. In the first part, I'm going to introduce the XXZ spin chain and this correlation function that I'm going to be studying. After that, I'm going to tell you about some results that are known, as well as our new results regarding this spin chain and this correlation function at this special point, delta equals to -1/2. We'll see what that means shortly. There's going to be a special eigenstate for these models that we're going to be able to construct using a set of equations called the quantum Knižník-Zamolodchikov equation. That will be the topic of section 3. In section 4, I'm going to define some very specific scalar products. They're going to be called inhomogeneous scalar products. Again, this will become clear what this word means soon. And the last part of my talk will be about how to take homogeneous limit of these scalar products. Also, this is my first time presenting via Zoom, so don't hesitate to ask questions, slow me down, write in the chat, and I'll be happy to answer your questions. Okay, so first part, emptiness formation probabilities in the XXZ spin chain. You can see my mouse, right?
Yes, we do.
All right, perfect. Okay, so I'm going to study this system. It's a periodic quantum chain. So this is my system. It's a periodic chain, and I have n of these spins around the chain. On each one of these sites, I actually have a space C2. So my overall Hamiltonian is defined on the tensor product n tensor product copies of C2. And this is my Hamiltonian. Okay, so you see there's a sum over J, and then you have some sigma matrices appearing here. So these, the sigma x, sigma y, sigma z, are the usual Pauli matrices. And when they have a lower index, it means that they're acting on the site number J, like sigma xj acts on site number J of my chain. So this Hamiltonian is the sum of a next neighbor interaction. So there's a sigma x interaction, sigma y interaction, and a sigma z interaction with the constant here, delta. This constant is usually called the anisotropy for my spin chain. Throughout my talk, I'm going to use this convention for the canonical basis of C2. So the state 1, 0 is going to be drawn as an up arrow, and the state 0, 1 as a down arrow. The simplest periodic boundary conditions that you can have on the chain, which is periodic, is that you see in the sum, when j is equal to n, we have some sigma x, for example, with an n plus 1. The simplest boundary condition is just to say sigma x n plus 1 is just sigma n1, right? So simply periodic. But here I'm going to consider something slightly more complicated, namely periodic boundary conditions, but with a twist. So it's going to involve a twist parameter phi. And so here we have sigma z, which is at n plus 1 is just sigma z1, but sigma x and sigma y are written as linear combinations of sigma x and sigma y. Okay, when phi is equal to 0, then it's purely periodic. This term disappears and this term disappears, and it's purely periodic. Okay, so this is the quantum chain I'll be studying, and the observables that I'm going to be studying are the following: the emptiness formation probability. So this observable is actually simply the probability that in the ground state of my Hamiltonian, I denote this ground state as psi. It's the probability that I have up pointing spins, which are consecutive in positions 1 to m. And I denote this by EFP, emptiness formation probability. N is the length of the chain, and m is the number of these spins that have to be pointing upwards. Okay, so this P is a projector. It acts in position K. Pk acts in position K. It's the matrix 1, 0, 0, 0, or just sigma plus times sigma minus. And this is basically one of the simplest correlation functions that you can compute for a quantum chain that you can study. In particular, if your model is critical versus if it's not critical, it will have a different behavior. So one way of defining it is like this in terms of a ratio of expectation values. but you can also write it in terms of the components of your ground state. So what do I call a component of psi? So I'm going to decompose psi in terms of, as a sum, in terms of the components in the canonical basis. So these alpha 1 and up until alpha n, they can take values up and down, and here I take their sum. And this number here, this coefficient, is what I call the component. So in these terms, the EFP is obtained as follows. So in the denominator, we have the sum of all the components, their absolute value squared. This corresponds to this norm here. And in the numerator, we also have a sum of components squared. But now it's a restricted sum because I only take the sum over the components where the first m spins are up. Okay, so this quantity actually has been studied for the last about 20 years. All right, and this slide gives an overview of the results that have been found. So the first two papers are about the free fermionic point and the XYZ model. So the free fermionic point is a special value where delta is equal to 0. In this case, the model, you can actually solve it explicitly using a Jordan-Wigner transformation. You can diagonalize the Hamiltonian exactly. And likewise for the XY model is a model similar to this one where delta is equal to 0, but here I have a different constant in front of the sigma y interaction. Okay. So in this case, these two authors, what they found that they could compute the emptiness formation probability when n is sent to infinity as a Toeplitz determinant. And in the second paper, they showed that it was actually related, these Toeplitz determinant, they're actually related to a Panev-5 equation. A second result, and this is going to be much more central for my presentation, is what happens at the combinatorial point. Delta is equal to -1/2. So as we're going to see, it's possible to compute the emptiness formation probability exactly for finite n, not just for infinite n, for every value of n and m which are finite. This result was first conjectured in this paper by Razumov and Stroganov in 2001. And the proof actually came later by Luigi Cantini, who's also a collaborator on this project. Two more results. The first one is that you can actually do a Bethe-Ansatz calculation of the emptiness formation probability for the XXZ chain for all values of delta when n goes to infinity. And the result is actually a somewhat complicated integral expression. It's actually a multiple integral expressions. And this was found by the Lyon group in this paper of 2002. Finally, last results. So by Korepe, Nokianov, Nishiyama, Shiroichi from 2003, what they did is they studied the asymptotic behavior when n and m become very large of the emptiness formation probability, and they were able to compute the first terms in the specific expansion when n goes to infinity. Okay, so this.
Alexi, il y a une question de Manu. Un instant, je ne sais pas. Manu, veux-tu...
Ma question était vraiment ta première transparent.
Yeah.
Shouldn't it be minus on both ones? I mean, you have cos and then minus sign, but then plus sign? Shouldn't it be minus? I mean, it should be a rotation, that's all.
It is a rotation, Manu.
Yeah, I think it is a rotation.
It isn't two negative signs?
No, I think you need to have one negative sign for it to be a rotation.
Okay, good.
John has a question too. John?
Yeah, yes, I thought that the point delta equals 1, the XXX model has special results.
So no, we'll see that it's actually -1/2. For delta equals to 1, I think this is also a special value. I'm not aware of results. I think possibly the results of Cantini and Maillet and Slavnov, they simplify at this value. But no, the very special point is -1/2. And I'll talk about this very soon in the next slide.
The XXX model, which is the
XXX
easiest of all.
is delta is equal to 1, indeed.
Yeah.
So this is not the point that I'm going to be studying. I'm going to be studying the value delta is equal to -1/2.
And is there, just to slip it in, I mean, the free fermion point is really delta equals 0?
Yeah.
And is that related somehow to the Ising model?
No, I don't think this is the Ising model. This is so. It's a bit different from the Ising model. The Ising model, in a sense, is a single fermion, and when you look at this free fermion point, you see that there are actually two fermions. So, for example, in terms of CFT, the Ising is C equals to a half, the central charge, and this is different. It's C equals to 1 because there are two fermions.
Okay, thanks.
Okay. Okay, so actually in my talk, the observable that I'm going to be studying is slightly different from the emptiness formation probability. We call it the boundary emptiness formation probability. So it's defined in a very similar way to the original EFP. We write it as boundary, so BEFP. It's again defined as a ratio of two sums of components, but we don't have the absolute values squared. They're just linear sums of the components. Okay, so this is the definition in terms of the components, but we can also write it in terms of a scalar product. So again, this psi is our ground state of the Hamiltonian. We act on it with projectors, and then the state that we put on the left is not psi, but rather it's another state, phi, which is just the n copies of up plus down. Okay, and likewise in the denominator, we don't put the norm, we put the overlap between psi and phi. So this is actually a new observable that we actually introduced. And so there are no previously known results for this observable. And actually for the spin chain, this is not really a probability, right? Normally a probability, you write it as a ratio of expectation values. So you need to have psi on the left here as well. But we'll see very soon why I call this a probability nevertheless. And this goes to the relation between the XXZ spin chain and another model called the six-vertex model, which is also a model which has been studied a lot, especially since the work of Baxter. So this one is a two-dimensional model, not only one-dimensional, it's two-dimensional. Here it's defined on the square lattice. And on this square lattice, every edge is actually occupied by an arrow that can point in two directions. Okay. An important feature of this model is the so-called ice rule. So the ice rule says that at every single one of the vertices, the number of in-pointing arrows is equal to the number of out-pointing arrows. With this constraint, there are actually 6 possible vertices which are possible. They're actually drawn here, 6 possible vertices. In the most general framework, one would like to define this model and give local weights to each of the 6 possible vertex configurations with 6 different numbers. But here we're going to study a very specific weighting for these 6 vertices given in terms of these functions a, b, c1, and c2, which are given here in terms of these 2 variables q and z. With this specific choice, what's going to happen is that our model is going to be integrable. So integrable models are quite interesting because for these models, well, in theory, you're able to compute everything. You're able to compute eigenvalues of the Hamiltonian, partition functions, correlation functions. But actually, in practice, there are only very few examples where correlation functions have actually been computed because it's quite technical. It's not easy. So these 6 weights, you can organize them in the R matrix. So the R matrix, it's a 4x4 matrix. Basically, it gives us the weights that we get from these vertices by saying that we say that there's a direction of propagation towards the upper right, and then we look at what comes in and what comes out, and we write the corresponding 6 weights in this way. And in terms of diagram, we usually draw this as a vertex with one parameter z assigned to the row and another parameter w assigned to the column. And then the R matrix is evaluated at z divided by w. Okay, so the fact that the model is integrable, actually, it comes from this Yang-Baxter equation satisfied by the R matrix. This is an equation on 3 copies of C2. Whenever I write R with 2 indices, it means that R acts on the copy 1 and 2 in this example, but acts as the identity on the 3rd copy. So this is a cubic identity for the R matrix. And this is really the equation that allows everything that I'm going to compute. This is sort of the master equation. Okay. So a key object for the 6-vertex model is the so-called transfer matrix. And here...
Alexi, il y aurait une question de John. John, tu veux poser la question? John, tu veux poser ta question?
Is phi an eigenstate of the Hamiltonian?
Psi is an eigenstate. Phi is not. Phi is not. No. Okay. So this transfer matrix, in terms of diagrams, it looks like one row of my lattice. Okay. So this row is assigned a weight W, whereas the columns are assigned are assigned numbers z1, z2 up until zn. These are usually called inhomogeneities. Okay, this is the inhomogeneous model. If it was homogeneous, then all these zi's would be equal together. Maybe all of them would be equal to 1. So its exact definition of this transfer matrix is the following. So this object in parentheses is defined on n+1 copies of C2. Okay, the copy number 0 is usually called the auxiliary space. So you take a product of these R matrices from right to left, and the arguments are Z1 over Z, Z2 over Z, and so on. At the end of this chain of R matrices, you apply a twist matrix, which acts only on this auxiliary space. And then you take the trace on the auxiliary space. So you get, in the end, something that acts on C2 to the n, or in other words, you get the matrix of size 2 to the power n. This object is useful for us because if you want to compute the partition function of your 6-vertex model on the cylinder has perimeter n and height L, well, then this is just the matrix element of your transfer matrix to the power L. And these states beta and alpha would be certain states that I would apply at the top of my cylinder and at the bottom of my cylinder. Because we have the Yang-Baxter equation, we can actually show that these transfer matrices, they generate the commuting family. So they commute when you change the parameter z, the first parameter. You see that sometimes I include the inhomogeneities, sometimes I don't. So if I keep the same inhomogeneities in the two copies, but change just the parameter z, then they commute. The reason why this is interesting for my XXZ spin chain is because there's a relation between my transfer matrix and my Hamiltonian, which is due to Baxter. So if I take my transfer matrix, derive with respect to D, and then apply the inverse transfer matrix, and I take the limit where all these parameters are sent to 1, I recover my XXZ Hamiltonian. So a linear combination of my XXZ Hamiltonian and an identity matrix. And the relation between the parameters in the XXZ model, this anisotropy, and the parameter Q in my 6-vertex model is the following. So delta is 1/2 Q plus Q inverse. So that's nice because I can get information from the XXZ model by studying the transfer matrix of the 6-vertex model. Okay, so I'm coming back to my correlation functions, my emptiness formation probabilities. So this is how they were defined, right? An expectation value of a product of projectors. One way to write this is as a limit as the following limit. So I apply some suitably chosen state at the top of my cylinder. I apply the transfer matrix L over 2 times. So here I make the assumption that L is an even number. I apply my M projectors. Then again, I apply my transfer matrix and then another state alpha. And then in the denominator, I divide by beta, t to the L, and alpha. It's the same thing as the numerator, but the projectors are gone. When I take the limit L goes to infinity, I recover precisely this first result. But in the second formula, it's clear that this is a limit L to infinity of a ratio of partition functions. So this is actually a probability. My emptiness formation probability in the 6-vertex model, its interpretation is that it's a probability that on an infinite cylinder, I have M spins somewhere in the bulk that are consecutive and aligned to be upward. So it's exactly this probability. The object that we've defined, the boundary emptiness formation probability, has a similar interpretation as a probability. But here, what we have is we have a semi-infinite cylinder, and then our states, which are imposed to be pointing upwards, are at the boundary. And then the other ones can be free, up plus down. So I have the state phi, which is at the bottom of the cylinder. So yes, both of them are probabilities. So now hopefully it's clearer why this BEFP, we call it the boundary emptiness formation probability. Okay, so we're almost at the end of my first section. But before I go on, I want to tell you one more reason why I believe that these emptiness formation probabilities are interesting. And it's because they're actually part of a family of observables where you can see a local phase separation. So local phase separations have been studied quite a lot in the last, say, 10 years. In particular, one such example occurs in the dimer model when you define it on the so-called Aztec diamond. So maybe you've already seen this figure before. You see that in these dimers, those that are in the corners are actually part of a frozen phase, while in the center, there's something that resembles more like a liquid phase. And there's actually been quite some effort in computing the limit shape of this form when the mesh tends to 0. In this case, it's actually a circle. So there's a local phase separation. Well, it seems that there's exactly the same thing happening or something similar happening for the emptiness formation probability. So this figure was actually taken from an article by Jean-Marie Stéphane from 2014. So what he did a Monte Carlo simulation on the six-vertex model, where what he did is at these two spins, these are sort of the endpoints of the chain of M projectors. So what he did is there's actually a map between the six-vertex model and a height function. And here he did a simulation, and what he plotted was the average value of the gradient of the height function. And you see that it also seems like there's two phases. But in this case, well, in the first case, we knew that this was a circle. In this case, we don't know what the curve is at the moment. So this is an open problem.
So is the boundary a hexagon?
The boundary here is not a hexagon.
Yeah, is that also liquid solid bounded by a hexagon?
So this model was defined, it's actually defined on the square, and this curve is not a hexagon. It's really it has a non-zero curvature.
No, I don't mean that. I'm thinking of that as the boundary of the frozen region.
So I think the boundary of the frozen region is this one.
Yeah.
And it's not a hexagon.
But if you add the solid region, does it become a hexagon?
Okay, this I'm not sure. I don't think it was mentioned in his paper. Okay, so now moving on, I want to tell you about results that we get at the combinatorial point. So recall the combinatorial point is this special value. Delta is -1/2. And here in the six-vertex model, we set Q to be this third root of unity, e to the 2 pi I over 3. Another quantity that will play a role in my explanations will be the total magnetization. So this is just the sum of all the Pauli matrices. And this is an operator that commutes with my Hamiltonian. So basically, we can diagonalize both of them simultaneously. And so we have the following theorem, which was initially conjectured in this paper by Razumov and Stroganov from 2001, and then later shown in 2006. So at this special value, at the combinatorial point, the Hamiltonian has a special eigenstate. And this special eigenstate, so it satisfies the following. First, the energy, so the eigenvalue of the Hamiltonian, is very simple. It's just -3n over 4. N was the length of the chain. And then the magnetization will have a fixed value in the following cases. So this eigenstate exists in two cases. The first one is n is odd. N is odd. Phi is equal to 0. That was a twist parameter. Phi equals 0, it corresponded to the usual simple periodic boundary conditions. And in this case, we actually have two states which are degenerate with this energy. One has magnetization +1. The other one has magnetization -1. That's the first case. The second case is when n is even. In this case, we have to set the parameter phi to be -π/3, and the magnetization is 0. And in this case, there's a single non-degenerate eigenstate. These three states, I'm going to denote them as psi plus n, psi minus n, and psi 0n. And of course, it's very easy to code this Hamiltonian in Mathematica for short chains. And then when you do that and you compute the corresponding eigenstates, you find the following results. So here, I give examples when n is an odd number. What you see, for example, for n equals to 3, psi plus is just a simple sum of the three components where they have exactly magnetization +1. Okay. Likewise, for psi 5, we get the sum of the 10 possible components. Some of them have a coefficient 1, others have a coefficient 2. Of course, in general, you can always change the normalization, but here the normalization is set such that the smallest component is just 1. It's easy to see that this state is actually invariant under translation. So maybe a shorthand notation would be to say that you have these two components plus all the possible translations. You can repeat the exercise for n equals to 7 and n equals to 9, and you find more and more components which have more and more integers. So already it's a surprise. It was a surprise that Razumov and Stroganov found that this special eigenstate, all its components are integers. This is really a non-trivial result. If you look at other eigenstates of the Hamiltonian, they will not have this property. So that's the first remark. Second remark, they're invariant under translation. I already mentioned this. And the third remark, here I only gave examples for psi plus, but psi minus is obtained from psi plus by just flipping all the spins. So this would be down, down, and up. And so that gives you psi minus. That's not the only thing they found in their paper. They found much more. In particular, they conjectured the following result, which was later proved in their 2007 paper. So if you look at the largest component of psi plus, so I already gave some examples, 1, 2, 7, 42. These numbers appeared in the previous slide. So what was eventually showed in this paper was that the largest component is the one which is the following, so up, down, up, down, and so on, and all its translations is given by the following number, capital A of n minus 1 over 2, and A small n is a number that you can write as a very simple product with a ratio of 2 factorials. So when they found this, they were quite intrigued because this is a number that was known in another area of mathematics and actually in combinatorics. It was known because this number also counts the number of n by n alternating sign matrices. So of course, that's stirred a lot of interest because they found a relation between something which came from statistical mechanics and something that was purely a combinatorial problem. So that's not the only result that they found. Two more results. You can compute the sum of the components, the linear sum, and actually the quadratic sum of the components. And you also get very simple numbers as product of ratios of integers. This number again appears, an and an squared. It's the same number that was here. Okay, so all of this, it's only for when n is odd, but there are actually similar results for n even. I'm not going to go through all the results, but I'm just going to give examples of the small eigenstates that you can see what they look like. In this case, they're not all of them are not just integers, but they're actually, the components are actually of the form a plus ib square root of 3, and a and b are either half integers or integers. Okay, so these are the first three states for psi 0, n equals to 2, n equals to 4, and n equals to 6. Okay. Remark number 2, psi 0 transforms very simply under translations. Okay, basically you just have to multiply by some specific power of q. Q is e to the 2 pi I on 3, and this number I think is actually minus q inverse. Okay. Third property, there are also known results for the sum rules and the largest component, like I gave on the previous slide for n odd. Similar results, they also found similar results. But in their original paper, they actually conjectured something even stronger about the emptiness formation probability. Recall how this was defined, an expectation value of a product of projectors. But now I add this extra label mu here, meaning I'm considering this observable for my 3 possible states, plus and minus when n is odd, and then 0 when n is even. So what they gave in their paper, and it was eventually proven by Luigi Cantini later on, was that they considered the following ratios: EFP, n with the number of up pointing spin n minus 1, and in the denominator they put it equal to m, and they find that it's a simple ratio of factorial numbers. Likewise, when it's instead mu, the minus eigenstate, and also for n even, they also have a similar result. This small n here that appears is just a way to parameterize the capital N for n even and n odd. And actually, this completely determines the emptiness formation probability, because we always have that whenever m is equal to 0, this result is 1. Right? It's easy to see here. In this case, there are no projectors in the denominator. So that gives the exact result for this correlation function. And this is really a non-trivial result, that they're able to compute this correlation function exactly for finite system sizes.
Alexi, John a une question. John? John, tu veux poser ta question?
Oui. Est-ce qu'il y a une symétrie ON?
Pas que je sache. How would this symmetry be realized?
Just look at the Hamiltonian. Just take all of the spin components and rotate them. I think it's invariant. It's a sort of dual symmetry. SL2 to the power n is dual to ON. Isn't
ON only satisfied for the XXX model?
I don't know. I'm just looking at the XXY, because the 3 components just transform independently. They're like scalar products. And so if you rotate the size, I mean, if you rotate the sigmas in the n-dimensional space of the vertices, then each individual term seems to be invariant. It's a scalar product.
Okay, so Okay, so what operator exactly are you suggesting to would make this
Replace
Hamiltonian?
sigma j as an n-component vector
Yeah.
by a rotation matrix acting on that n-component vector, and do the same thing. I mean, I guess that's not going to be the same. Actually, it's not a scalar product. It's j plus 1.
Yeah, so I don't think it has an ON invariance. I don't think it does.
Yeah, maybe not. J plus 1.
Okay,
Yeah.
so
Okay.
so this was the result from 2012, and then our new result is about the boundary emptiness formation probabilities, where now the state that we put to the left is again this state phi up and down, and then we also find we're also able to compute these correlation functions exactly. We have not written it in terms of, I haven't written it here in terms of a ratio like on the previous slide. Instead, I wrote it the explicit form in terms of this double product. And so our result holds both for the plus, minus, and zero eigenstate when n is even and odd. Okay, so initially when we actually found this result, when we conjectured it, we found it in a form that was similar to this. And eventually when we proved it, we found these very elegant forms. So this is the one that I'm presenting. In the rest of my talk, I want to explain how we managed to prove this. So it's actually quite a nice calculation. And the strategy is the following. So our goal is to compute these spin chain scalar products. Okay?
Can I just interrupt?
Yes?
Yeah. Why do you call it this boundary emptiness something probability formation?
Okay. So as I mentioned a bit earlier, its interpretation in the six-vertex model is a probability that you have a semi-infinite cylinder with some arbitrary state at the top, but the state at the bottom is the free state, so up plus down. And it's the probability that you have m consecutive spins on this boundary. This is why we call it the boundary emptiness formation probability. Okay, so
what is the emptiness? I don't.
So I think that they usually consider that in these spin chains, whenever you have a consecutive chain of up arrows, it's a bit like a consecutive. It's imposing that the part of your lattice has no correlation, right? It's sort of this one is completely fixed, so no correlation. That's why I think that's where the emptiness comes from.
It's ferromagnetic. It's completely correlated. No?
Yeah. Okay. But
okay. Fine. Good.
If I could say, I think it's related to the Jordan-Wigner transformation.
Okay.
Right? Because Jordan-Wigner, to have a sequence of upstates would be to have a sequence of holes. I mean, plus minuses. So there would be. It's just another interpretation, but maybe that explains the terminology.
Okay. So our strategy. So what we want to do is we want to compute these scalar products in the spin chain. The strategy that we use is perhaps counterintuitive. It's to actually make the problem more complicated by looking at a similar problem for the inhomogeneous six-vertex model. So inhomogeneous means that we have these extra parameters, z1 up until zn. We'll see that in this case, there's also a special eigenstate of the transfer matrix, which we can construct using the so-called quantum Knieznik-Zamolodchikov equations. So that's going to be the topic of my next section. After this is done, I'm going to tell you how we define overlaps, which generalize the spin chain overlaps to the inhomogeneous case. And the last step will be to compute the homogeneous limit. So this is sort of the outline of my sections 3, 4, and 5 in my talk. So I start with the quantum Knieznik-Zamolodchikov equation. Okay, so the first result, again in this same 2007 paper, is that, all right, so we fix Q to be this third root of unity, and then we consider the three cases as before, 0 for n even, plus and minus 1 for n odd. And we look this time at the transfer matrix. Okay, so the transfer matrix, the inhomogeneous transfer matrix, the theorem says that there's a state, psi, of magnetization u. So this psi is capital psi. It's different from the one I had before, which was a smaller psi. Okay, so there's this eigenstate of the transfer matrix, which has the eigenvalue 1. Okay, and then it has a magnetization u, like the small psi had. So if you code the transfer matrix in Mathematica, you can compute the first few the first few of these eigenstates. And you see that, of course, they're a bit more complicated. For example, for n equals to 3, they're not just 1, 1, 1 times the 3 components, but they're actually polynomials in these inhomogeneity parameters, z1, z2, and z3. Likewise, for the state capital psi minus, 3 polynomials. And for n equals to 4, another example, it has 6 components. Here I wrote only 3. In some cases, it actually factorizes, but there are also some non-trivial polynomials that occur. Okay? And so in the following slides, I'm going to tell you how we can construct these polynomials. But before that, I'm going to tell you some of their properties. So first of all components are polynomials in the Zi. This is, again, something non-trivial for the eigenvalue of a transfer matrix. In general, you would have square roots and so on. We know exactly what the polynomial degrees are for each of the Zi. Whenever n is odd, the degree is n minus 1 over 2. When it's even, it's n over 2. A very useful property is this one. When you take the homogeneous limit, so the homogeneous limit is we take this capital psi, set all the Zi's equal to 1, and then we recover the small psi, which was the eigenstate of H. I'm going to draw this one in terms of, I'm going to use a diagram for this one, for this state psi. It's going to be this diagram, okay? And we'll see why this is useful in a bit. With this diagram, the eigenvalue equation is the following. So we have the transfer matrix acting on my state capital psi, and the result is just the state capital psi with the eigenvalue 1. Okay. All right, so how do we construct this state psi? So it's constructed using the so-called quantum Knieznik-Zamolodchikov system. So this system is composed of two sets of equations. The first one, the exchange relations, and the second one, the action under translations. The exchange relations, they involve a matrix called the R-check matrix. So this R-check matrix is similar to the R matrix, but I applied a permutation operator from the left, whose action was basically simply to interchange the order of the rows 2 and 3 in this matrix. I'm going to draw this operator as using this diagram. Okay, so the exchange relation says that if I take my state psi and I apply the R-check matrix acting in position I plus 1 with this argument, then I recover psi, except that Zi and Zi plus 1 are interchanged. In terms of diagrams, this is a diagram. I have my state psi. I act on it with my R-check matrix acting in position 2 and 3. And then the result is, again, psi, where Z2 and Z3 have been interchanged, right? So it's very easy to read the result from this diagram. Okay. So that's the exchange relation. There's also a second relation, which is the action under translation. So tau is the translation operator. When you act it on a state of the canonical basis, it simply translates your state towards the right by one side. If you take this operator and act it on this eigenstate psi, capital psi, it translates all the z, the z1, z2 to the left, except actually the first one is actually sent to the end and multiplied by a power q to the 6th. On top of this, you have to multiply in front by an operator which acts only on the site number n. So for example, for the eigenstates that I'm going to be interested in, for the even n, this is the formula for dn0. It's slightly different for d plus and d minus, but it's just minus power of q and then q to the sigma zn. Okay, so you might wonder why does, for my third root of unity, why is this exchange relation satisfied? So I'm going to tell you a bit more about this. So why do we have the exchange relation for the special value? Well, actually, you can show that the inhomogeneous transfer matrix satisfies this relation. So T of Z, we multiply it by an R-check matrix acting in position I and I plus 1 with this argument. Well, then you can actually move through this R-check at the cost of interchanging in T the Zi and Zi plus 1. So if you draw this in terms of diagrams, this is the transfer matrix. This is the R-check matrix in position 2 and 3. And then I can simply commute it through, but the result is that Z2 and Z3 have been interchanged. So this equation is actually, this is actually due to the Yang-Baxter equation. I didn't draw it in terms of diagram, but this equals to this is exactly what the R matrix, what the Yang-Baxter equation looks like in diagrammatic form. So the good thing about the exchange relation is that it's actually a local relation, right? The operator R-check of I plus 1, it's a local operator. And the exchange relations, they give us some very strong constraints for what the components of capital psi can be. particularly if I consider psi, its components I and I plus 1, if both of them are up, then I can show that it satisfies this equality, right? On the left-hand side, Zi and Zi plus 1 are ordered as usual. On the right-hand side, their order is interchanged, and then we have these simple prefactors on the left and right. We have the exact same identity when the two sides are down instead of being up, the same prefactors occur. But perhaps more interesting is the following. If we look at a component where in the I and I plus 1 position I have down and up, then I can actually compute this one from the component where in I positions I and I plus 1 it's up and down. And then I have to act on it with a so-called divided difference operator. And this divided difference operator delta I, this is its action on a function f of the two variables Zi and Zi plus 1. So it's a linear combination of these two f's. One of them is just the usual f, and the other one is the f where the two arguments have been interchanged. And then we have simple polynomial here, and likewise one in the denominator. And you can show that this divided difference operator actually maps polynomials to polynomials. Okay, so that's very nice because this allows us to construct our state capital psi using these two steps. So here I'm going to give the example when n is even and u is equal to 0, but this also applies for the other two cases. First step, I fix the polarized component. Okay, the polarized component is this one, up, 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 down, 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 down. I fix this one such that it has this product form. This product form is actually a nice choice because actually with this product form, it satisfies the first two equations. That's quite easy to show. And also I've included denominators in such a way that if I set all the zi's to be equal to 1, well, the result is simply 1. This is what I want in my homogeneous limit for my eigenstate of the Hamiltonian. And so that's the first step. The second step, I can construct all the other components using the divided difference operators. Okay, so for example, whenever I have a down and an up, well, I can compute it using this operator acting on the same component, but now with up and down. So this actually allows me to construct all my components recursively. So this is actually quite simple to put on Mathematica and to have it construct these eigenstates of the transfer matrix. It's much more complicated to code the transfer matrix and to ask Mathematica to diagonalize it. This is a much easier way. And actually what was shown in this 2007 paper is that at this root of unity, these polynomial solutions of the QKZ equations, they actually coincide with the special ground state of your transfer matrix. That's a very useful construction. It's very useful because already we know how these states psi, how they behave under exchanges of these inhomogeneity parameters from the exchange relation. Another very key property for our calculation is that these...
Je peux t'interrompre, il y avait une question que j'ai oubliée. John a levé sa main depuis un petit bout de temps. John, tu peux vous...
Sorry to ask so many questions, but
okay.
So I'm familiar with the usual Cauchy-Zamolodchikov equation, and I didn't quite see how that relates to your quantum Cauchy-Zamolodchikov. The usual one looks like a bunch of, with a square root of -1 missing, a bunch of Heisenberg type equations which say that commuting Hamiltonians HI acting on the state is equal to some constant times the time derivative. Now I presume that there is a quantum version of that where instead of a differential operators you have these divided difference operators. But did you actually write down what the quantum Cauchy-Zamolodchikov equations are?
Okay, so my knowledge is that these are actually the defining quantum Cauchy-Zamolodchikov equations. I'm not sure how they relate to the classical case that you're describing, though.
Well, I think of the classical case as a bunch of compatible time-dependent Schrödinger equations in the Heisenberg representation. So what's evolving actually is the operator, but you can write it on a state if you like, by just making a unitary transformation from between the Heisenberg and the Schrödinger representation. But it is a bunch of compatible differential equations. Now, this is not just, well, this is a set of some kind of difference equations, I guess.
Yeah.
I'm not quite sure.
So similar to this. So this seems to be, yours seems to be a continuous version, and this seems to be a discrete version.
I should just slip in a very interesting fact, but probably you're not interested in this aspect. The ordinary Cauchy-Zamolodchikov equation can be thought of as a quantum isomonodromic deformation equation. So it's I don't know if the Q KZ equation also has an interpretation in terms of isomonodromic deformations, but that is an isomorphism. It's just a way to see it. Do you know anything about that?
I don't know anything about that.
Okay, so sorry, don't want to change the subject.
All right.
Alexi, in the last slide that you discussed, this one, the two products, they look identical. Is that what you meant?
The difference is that is the bounds. Right? The two products are actually identical, but one of them runs from 1 to n over 2. So
Okay. So the ij, okay, I understood. Okay. Thank you.
All right. So one key property is the exchange relation. Another useful property that is the following. It's a reduction relation, a reduction property. And this is a property for whenever you specialize the last inhomogeneity to q squared times the one before that, so z to the n minus 1. When you do this, so what you obtain is some function, some simple polynomial in the zj's, times the following. So you get the solution of the quantum Kniznik-Zamolodchikov with n replaced by n minus 2. And actually, it's tensor product with the two-state site, omega. And this omega is just up, down, minus q inverse, down, up. And this reduction property can actually be traced back to the fact that when you look at your R-check matrix and you evaluate z, or its argument to q to the minus 2, well, this R-check matrix has 3 zero eigenvalues and only one eigenvalue, which is non-zero, and its image is precisely omega. So if you do the calculation, you see that this reduction property comes from this property of the R-check matrix. This is going to be useful shortly. So now I'm at the point where I want to define inhomogeneous scalar products. Okay, so recall that my goal to compute my boundary emptiness formation probability is to compute this sum, right? This sum of components, right? I'm going to call this sum CNM, 0, focusing on the case when n is even. Okay. Once I've computed the sum, I'll be able to take the ratio CNM divided by CN0, and this will give me the boundary emptiness formation probability B, E, F, P, M, N. Okay. So I can write this as an overlap. I get my eigenstate of H, and I apply it. I take the scalar product with the following states. So first, M consecutive up arrows, then up plus down tensored n minus m times. Okay, so this is what I want to compute ultimately. But now I'm going to lift this to an overlap in the inhomogeneous model. I'm going to call this S0 n. So instead of having my small psi, I have my capital psi. I'm going to describe this in a second, that its inhomogeneities are going to be specified in a specific way. And I'm going to apply to the left a state. Gamma m is this number here, and then p is n minus m divided by 2. In practice, I could choose this state to be the same as I had before, but actually I'm going to choose something a bit different, and it's going to be useful for a reason that will be clear soon. So instead, I'm going to focus on the case when also m is an even number. We also have the result when m is odd. It's a bit different, the construction, but it's similar. So this state gamma mp, it's again a sequence of m consecutive upwards pointing spin. This is unchanged compared to what I had before. Then the rest is a tensor product of the state psi that depends on the xi, x1 up until xp. And these are actually two states, two spin states. So that they live on C2. So the general definition of psi of x is a linear combination of these 4 states with 4 numbers kappa 1, kappa 2, kappa 3, and kappa 4, which are going to be functions of x. And they need to have this property. When I said x equals to 1, they need to be up plus down tensored twice. Okay, so in terms of diagrams, it looks like this, right? I have my eigenstate, and then I take the scalar product with this state that has m consecutive up spins, and then p copies of this chi of x. So this is chi of x1, chi of x2, chi of xp. And we see that we fix the inhomogeneity such that when we have up arrows, the inhomogeneities are z1 up until zm. But then when we have chi, we set them to chi of x, we put x and x inverse, and so x2 and x2 inverse, and so on. This is the quantity that we're going to compute. I haven't yet told you what kappa 1 to kappa 4 is, but this is the topic of the next slide. So we choose this state chi, in such a way that it satisfies the boundary Yang-Baxter equation. So we can write this equation as a formula. So this is the formula. We can also write it in terms of an equality between diagrams. So I always find it's easier to understand this way. So this equation tells us how we can interchange the order of these chi x and chi y, right? So chi x and chi y, if I multiply them by two R-check matrices, I can interchange the order and then multiply by two other R-check matrices. Okay, so in vector form, it looks like this equation here. So this equation is well known. There's actually a well-known three-parameter family of solutions to this equation. And here we're going to consider one very specific solution, which is the following. So it depends on the parameter x, as announced. And it indeed has the property that when we specify x equals to 1, here we get up plus down tensored twice. Okay, so we'll see in a second why this is a useful solution. So with this construction, we have several properties of the overlaps that we understand. The first, we understand its polynomial properties. It's a polynomial in each of my zi's, and we know its degree. It's n over 2 minus m. Okay. Second property, it's a Laurent polynomial in the xi parameters, and we know its degree width. It's n over 2. So the degree width of a Laurent polynomial is the difference between its maximal and its minimal power. Okay, moreover, we have some symmetry relations. If we interchange zi and zi plus 1 in s, we get just s without the interchange, but we have to multiply by this factor. This comes from the exchange relations directly. Second symmetry relation, s is actually invariant under the exchange of xi and xi plus 1. And this is actually because we chose chi to satisfy the boundary Yang-Baxter equation. Otherwise, that would not be true. A last symmetry that we have, it's invariant if we change x1 for x1 inverse, for example, or xi for xi inverse. So symmetry relation. There are also some reduction relations. If we specify the last x in term as q minus 2 xp minus 1, then we get an overlap where n is changed for n minus 4. And then this is actually a function. I didn't write it. It's a simple function of the zi parameters, but it fits on 3 lines, and I thought I would spare you this pain of looking at this function. A second reduction relation. This is when if I set 2 of my z's to 2 of the x's in this specific way, then I get another overlap. Again, n goes to n minus 4, and then m goes to m minus 2. And this is another simple function. Okay, but probably the most important property is the last one. All these the 4 first properties, they actually fix uniquely s. And that's rather easy to understand why. S is a polynomial in xi, for example. So for example, in xp, it's a polynomial. I know its degree. And if I want to fix this polynomial uniquely, I need to be able to compute it at n over 2 plus 1 values. This one here gives me 1 value, but it's not the only one. I have many more because I have these exchanges. And it's easy to check that actually with these relations, I have enough values that I can evaluate it at to fix this polynomial s uniquely. So from here, what we need to do is what we did is we actually found a candidate expression that satisfies all these relations. And then by the uniqueness, this candidate expression will be the correct expression for our overlaps. And so this is what we found in our paper. This is the first result with Christian and Luigi. Again, for Q a third root of unity and P this number, then our inhomogeneous overlap is given by this formula. So it looks a bit complicated, but actually the first part up until here is actually quite simple. It's just a simple product of these functions, polynomials in xi and zj. The non-trivial part is in this part here with the determinant of a matrix. Also, there's also a denominator with 2 functions. So these 2 functions, these 2 C functions, are the following. So C of y1 until yn is a product of I smaller than j, yj minus yi, and then we have yi, yj minus 1. The matrix M is a really non-trivial matrix. It's actually a matrix that's divided in 6 blocks, 2 of which are 0. And the blocks are given in terms of certain functions eta. And instead of describing this, I'm going to show you an example. It's going to be simpler by looking at an example. So here's my example. N is equal to 14, M is equal to 4, and P is just 14 minus 4 divided by 2. P is equal to 5. So this is the matrix M45. It's a matrix which has 6 blocks. 1, 2, 3, 4, 5, and 6. 2 of them are indeed 0. If you look at the first block, you see that the difference between the rows is simply you change x1 for x2 and x3 and so on. If you look at different columns, you see that the denominator is the same, but the numerator changes. You have always a sum of 2 powers of x1. What about the block number 4? The block number 4 actually really looks like block number 1, except that we have a minus sign. We have a minus sign in the numerator, and likewise in the denominator. Okay. Likewise for the bottom 2 blocks, this bottom left block, block number 5, is actually very similar to the first one, except that the z's are changed for x. And likewise, the block number 6 is similar to block number 4, whereas x are changed for z's. Okay, so this is the result. It's a rather complicated result, and you might wonder how we found this. And the way we found this was actually, well, we studied the recursion relation for our overlaps, and we saw that they're actually related to recursion relation for so-called even orthogonal Schur polynomials and symplectic Schur polynomials. And actually, the left part of this matrix, if it was a square matrix, it would look like it would be exactly the form of a even orthogonal Schur polynomial, and on the right, it's a symplectic Schur polynomial. So I won't go into more details for this. This brings me to the last section of my talk. We want to compute the homogeneous limit. So recall, the homogeneous limit is we take all the x and z parameters to 1, and then we recover our homogeneous overlap. So the non-trivial thing to compute is this limit with a determinant. So here there are some other prefactors which I've removed. So I've used this symbol to say that some prefactors have disappeared. But the non-trivial part is this determinant. Okay, so indeed, if I look back to my determinant, to my matrix, we see that if I set x2 equals to x1, well, the determinant of this matrix will be 0. But then this is compensated by the functions c in the denominator, which are also 0 if I set x1 equals to x2. So this is a non-trivial limit to be taken. Okay, so I'm not going to show you how to do the exact computation, but I'm going to show you the idea behind this computation. Imagine that you look at this toy example. You want to compute this quantity j, which is a 3×3 determinant, where you have 3 functions, f1, f2, and f3 for the 3 columns, and 3 variables, x1, x2, and x3 on the 3 rows. And then you divide by this polynomial. And you want to take the limit where all 3 of these are sent to 1. So I'm going to do this computation, and I'm going to suppose that these 3 functions have well-defined Taylor series around the point x equals to 1. The first thing I can do is I can evaluate the first variable, x1, rather easily, right? I just replace x1 by 1 everywhere. The next thing I can do is now I want to do the second line, x2 to 1, and I'm going to use the Taylor series for the 3 functions, f1, f2, and f3. The Taylor series around x equals to 1. When I do this, well, of course, I get a first term, f of 1, and likewise here and here, which I can remove by taking a linear combination with the first row. When I do this, I'm left with this, with the remaining expression for the Taylor series. And of course, this x minus 1 can be factored and simplified with this number. And then when I take the limit, I just get the first derivatives on the second row. So that was rather easy. I can repeat the next step for the next one, but now I need to go up until the second order. And when I do this, I obtain a matrix where on the third row, I get the second derivative. There's a factor of a half, simply because in my Taylor series, I have a factor of a half. Okay. So this I have to apply to my complicated 14×14 matrix that appeared earlier. So of course, there are some intermediate steps, but when I do this correctly, I get a 14×14 matrix, which is the following. Some steps, I haven't told you about some steps, which were taking linear combinations of rows and columns. But basically what this did is that as a result, we don't have any blocks which are zeros. We get a very nice matrix written in terms of 14 numbers, which here are written here. They're divided into 2 sets. The first set, minus 60 up until minus 20, you see that they always jump by 6. And likewise for the second step, and now starting at minus 18. Okay, so this matrix, if you look at it further, of course, to each row, there's a V1 or VI for each column, sorry. And if you look at the entries of the matrix, you see that the powers of V, they increase linearly until at some point they start jumping by 2, right? And the number of times they jump by 2 is precisely this number m here. So this was n and this was m. So such determinants they have been studied before. They're related to Schur polynomials. So Schur polynomials is the following. So it's labeled by a partition, lambda. So partition is a sequence of integers. Here I have n of them, which is decreasing. Often we draw partitions in terms of Young tableaus. So here you have the partition 6, 4, 4, 2, 1, 1, 0. See that I have 6 blocks, 4 blocks, 4, 2, 1, 1, 0. This partition here, I'm going to call a staircase partition, right? You can clearly see why, 5, 4, 3, 2, 1, and then I put 3 zeros at the end, 0 to the power 3. So the Schur polynomial S lambda is defined as follows. It's a ratio of 2 determinants. In the denominator, I have the van der Waals determinant. We know how to write this as a product, but here you see that the powers of x, they grow linearly from 0 to L minus 1. In the numerator, it's different. They grow according to the numbers in the partition. Okay. So it's actually easy to see that this ratio actually produces a polynomial, not just a rational function. And actually, our determinant that we wanted to compute is actually, you can actually write it in terms of a Schur polynomial. So there's a prefactor here, which is simple. Then S of this partition. So it's a staircase partition. It starts at m and decreases until 1. Then you have 0 n minus n times. And then you have these v. These were the 14 numbers that you saw in the previous slide. So the last part of the calculation has to do with Schur polynomials, how to evaluate certain specific Schur polynomials. Okay, so, and what we did is we derived 2 results for the Schur polynomial that have a staircase partition. First result, proposition 1, reduction relation for a Schur polynomial for a staircase Schur polynomial. So this is the staircase, a minus 1 up until 1, then 0 to the b. If we set the x1 to be equal to 0, we can show that this Schur polynomial actually just reduces. We can just amputate b by 1. And then this x prime simply means that the variables are, instead of being x1 to xl, they start at x2. Second result, if we have opposite sign pairs, x2 is equal to minus x1, we can also reduce the Schur polynomial to a smaller one, where b is replaced by b minus 2, and then the x parameters start at x3, x4, and so on. That's the first result. That's quite useful because if I go back to my matrix, we see that the second set of numbers, one of them was 0, and the other ones are related by pairs that have a different sign. This allows me to reduce my determinant to a smaller determinant of size 7 instead of being of size 14. That's already a simplification. The second result is an evaluation for staircase Schur polynomials when the variables are equally spaced. Okay, xi is alpha some constant plus a second constant times I. Okay, and then in this case, we were able to evaluate these polynomials explicitly. So with all of this, we have our final result, which is we're able to compute this homogeneous overlap. It's this product. Okay, and then once we have this, we take this ratio and we compute the boundary emptiness formation probability. And this is the final product form. And so here I told you how to do this when n is even and m is even, but actually we also did it for when m is odd and when this number is even. So actually this is actually just 1/6 of the computation we did. So this brings me to the conclusion. So what we did in this work is we defined and we studied a new correlation function, the boundary emptiness formation probability. And our main result is that we were able to compute it exactly at the combinatorial point, and for finite m and finite n. So future avenues for future work, you can obtain similar results if instead of considering the XX chain with periodic boundary conditions, you consider open chain. Also, we would like to understand the asymptotics of this new quantity, just like the asymptotics of the emptiness formation probability was understood using quantum field theory arguments. And finally, another open problem is to understand these Arctic curves that I showed earlier for the EFP, but also for the boundary equation. So this ends my presentation. Thank you very much for your attention.
Merci beaucoup, Alexi. Thank you. Is there time for questions? Any questions? John has a question. Go ahead.
Okay. So you started with the XXZ chain. You pointed out the correspondence to the vertex model, and then you went to the inhomogeneous vertex model, asymptotics, and then you took a homogeneous limit.
That's correct.
Is there, for the inhomogeneous vertex model, is there an equivalent spin chain?
Not that I know of. I think, hang on. Well, okay, so if I go, hang on. Okay, so of course, for the inhomogeneous model, you can do the same thing. You can take the you can decide that you'll study a Hamiltonian where we don't set the zi is equal to 1. right? And then just to say we're going to define an inhomogeneous Hamiltonian. But what I think will happen here is that you're going to get a sum of non-local operators, which is going to be highly non-trivial. So I don't think it's going to be a very interesting spin chain if you do that. You can do this, but you're going to have long-range interactions in your quantum chain.
The Godin model has long-range interactions. It's an integrable system.
Yeah. Okay. So then maybe the answer to your question is yes, you can do this.
But this is integrable. Are these integrable for the inhomogeneity parameter?
They are integrable because this matrix, this equation still holds, right? T of z commutes with T of w, and then the result is because H, you obtain H by a derivative of T. Well, H also commutes with these transfer matrices. So yes, it is still integrable.
Thank you.
Nicolas, you have a little icon beside your name. I don't understand this icon. Did you want to ask a question? Probably not. So I'll give Manu, you can ask your question now. Nicolas, go ahead.
J'avais pas de question.
Ah, tu n'avais pas de question. OK, merci. Merci d'être là de toute façon. Et on va donner la parole à Manu. Manu?
Hi, Alexi. You had these twisted boundary conditions, right?
That's right.
Is there a soliton involved then in the ground state? And I mean, if so, shouldn't the ground state be massless, so-called?
Okay, so this model is actually I think okay, so this model is actually well studied. And it's known that in terms of this parameter capital delta, this anisotropy parameter, when delta is between -1 and 1, it's usually called the massless regime. This massless regime means that when you consider not just the ground state but the excited states, as n increases to infinity, the gap between your eigenvalues tend to 0. So this is usually called the massless regime. But when you go outside this interval,
with the twist.
Say that again.
With the twist.
With and without the twist. Okay. When you go outside this interval, so when the absolute value of delta is bigger than 1, then it's actually massive. And when you look at your eigenstates, and you look at, for example, the difference of energies between the first excited state and the ground state, it doesn't converge. The difference doesn't converge to 0. It converges to a non-zero quantity. I'm unaware of an interpretation of this in terms of a soliton.
And may I say something? This is perhaps totally coincidental, but Manu is talking, I guess, about quantum solitons, but it's a fact, very well-known fact, look up my book, or our book with Ferry, who is here, that if you take the staircase partitions and the Schur functions for that, it exactly gives you the rational solutions, so they're not solitons, they're rational solutions of the, what is it, Ferry, is it the KP or the KDV hierarchy? Okay, I don't know if that answers there, but anyway, it's it's either the KDV, which is a reduction of the KP. Now, those rational solutions, of course, are not solitons, but they are degenerate solitons where you allow branch points to coalesce. So that's just a coincidence, but that is a classical integrable use of staircase partition Schur functions.
Okay, so here in our case, they correspond to certain inhomogeneous overlaps in our model. So I'm not sure, I'm not sure exactly what the relation is.
In the classical case, they are the solutions to the equation.
Okay, I've seen that some people have opened their microphones. Someone would like to ask still a question. If not, I'll open all the microphones and offer thanks to Alexi. Thank you. And next week, I think, let me see, I think it's Joris van der Jagt, let me check. Yes, next week is Joris van der Jagt from Ghent. So thank you very much, Alexi. That was nice. And see you next week.
Thank you.
Thank you.